Hello again, distance learners of 6th grade. This is Mr. Wallace coming to you from the planetarium here on day 2 of our planetarium time. And I'm wondering if you can figure out what the topic of today is going to be by looking at your screen. Some of you may know that this looks very much like the surface of a star, and you would be right. So our topic is going to be all about stars today. And a lot of specifics about our sun, and the different things that we know about our sun, and how our sun compares to other stars. So what you are looking at here on your screen is actual video of the surface of our star, the sun. It is a time-lapse photography sort of video. But it does a really cool job of showing us what's going on the surface of the sun. And it's not just static. It doesn't just sit there. It's not smooth by any means. It is constantly changing. And what you're seeing here is big plumes of energy that are spewing up into space, thousands of miles up into space. And one of the things I want you to realize is how big our star is. It is incredibly huge compared to planet Earth. The diameter of planet Earth is about 8,000 miles. The diameter of our star, the sun, is 800,000 miles. So it is incredibly huge. But the interesting thing, I think, is that it's made out of gas, not solid Earth. Not solid ground like Earth is. It's made out of gas, and you have studied recently, I believe you have studied the periodic table, right? And so you might know that gas is very light. The first element on the periodic table is hydrogen. And that's what it turns out stars are made of, is hydrogen. But they're an amazing amount. The amount is amazing, the amount of mass that we're talking about here. Even though it's hydrogen, and it's the lightest element that we know of, there's so much of it there, it makes for an incredible mass. It's the most massive thing in our solar system by far. It's not only 800,000 miles in diameter compared to 8,000 for the Earth, but it would literally hold over 1 million Earths. If you cut the top of the sun off and pour in Earths, it would be over 1 million to fill it up. And that's just, I mean, you can't even imagine that. You can't even fathom how big that must be. But we've studied the sun's surface for a very long time, and what you're seeing here is video from a telescope that does nothing but studies the surface of the sun. And you'll see that it's constantly changing here on your screen. There's different views, there's different filters that are put onto this telescope and gives us a different look at the surface. But it's constantly changing, and things are erupting off of the surface. But what's happening is that hydrogen that makes up this huge ball of gas, what's happening is that hydrogen is being forced into an incredible pressure, unimaginable pressure in the inside of our star. And what that does is it creates what's called nuclear fusion. And you'll see that in the show that you're going to see today a bit. And what happens in that nuclear fusion then is that energy is released. It's like an atomic bomb. And that energy is released into the different layers of the sun, and eventually it reaches the surface of the sun, and then we see that as light, we feel it as heat and radiation and so forth that reaches planet Earth. And this process continues for billions of years. And so how old is our star? How old do we know that our star is? Well, we know that it's about halfway through its lifespan. And that's about 5 billion years, okay? So we think it's going to be able to consume fuel, or the hydrogen, over the next many billion years, up to 5 billion years. And in that time, the sun's going to go through, changes along the way, and who knows how it'll affect Earth. And even just 1,000 years from now, how is the sun going to be doing when it comes to giving us life here on Earth? So anyway, let me show you something different. I could watch this for a long time and watch how the surface of the sun completely changes over that amount of time. But let's move on to something different. I would like to show you something called the HR diagram. Now, the HR diagram is something that was created, well, it was a little over 100 years ago, and it was created by two men. Their last names were Hertzsprung and Russell, and therefore they called it the HR diagram. Now I'm going to use my cursor here, and I think that will help show some things. What they did, they were astronomers in their day, and they decided to take what we knew about stars and plot that information on a graph. We could measure their size, we could measure their brightness, their temperature, their color, and so they decided to make a graph, and this graph is still studied today. And in fact, when you get into 8th grade, you will study it quite in depth. But let's just take a quick look at it, and then I'm going to let you see that show today about our sun. But let's focus on the HR diagram for a sec. What you are seeing on your screen is, and sorry I have to kind of look up here at my other screen, but along the bottom you will see that Hertzsprung and Russell decided to plot the temperature of stars along the bottom. And you'll also notice this K right here. This K is like another way to measure temperature. It's like Fahrenheit and Celsius, but it's its own scale, and it's called Kelvin. And the numbers get pretty extreme, and as you can see here, we have anywhere from 30,000 all the way down to 3,000, and that's kind of interesting in itself. The numbers go down as you go further out on this bottom axis, and normally that would build from like 0 and go up, right? But in this case, what they wanted to do was to plot the temperature from the hottest near the center right here to the coolest way out here on the edge. And so we go from 30,000 degrees Kelvin down to 3,000 degrees, and then everything in between. You will also notice that the color along the bottom changes as the star gets cooler. And think of a campfire or a flame of some kind. The hottest part of the flame is always the bluest part, right? Well, it works that way with stars. The hottest stars that exist out there are the blue ones. And if you go out any night that's clear and you look up in the sky, you can spot some of those blue stars. You can also spot some of the red stars that would show up over in this range, and they are the cooler ones. Now, they're not by any means cold, but they are cooler than the hottest stars. And then everything in between, and you can see that the the different colors change as the temperatures change on this scale as well. Now over here on the left, or the axis that goes up right here, you will see that this measures this fancy word called luminosity. And it's nothing more than the star's brightness. How bright is the star? And well, so what do we compare that with? Hertzsprung and Russell decided to compare it to our star. So they put our star, the sun, right here. And right along this this line, that if we could draw a line here, it'd be right at the 1, okay? So our star's brightness is on the scale, and it's at 1. Our star's color is right here in this G-class yellow star range. But over here on this luminosity, if 1 is here, then anything below this, any stars that are below our star here would be dimmer stars, and then any stars that are way up in this range would be brighter stars, and up to 1,000,000 times brighter. Okay, that's pretty incredible to think about that. But even if they're at this range, they're 100 times brighter, which is mind-boggling in itself. So we've got brightness along this scale, we have temperature along this scale, and they also knew sizes. So you're going to see this, when I put more stars on here, you're going to see the stars are smaller or bigger, and then you're going to see their color, you're going to be able to look across and see their brightness and look down and see what their temperature would be. So let us continue here and see what Hertzsprung-Russell did as they plotted all of these stars. You'll see here comes a small one, a little bit bigger there. I'm going to let this sort of fill in. And names of stars appear. Some are numbered, some are just the names of the stars. Scientists have given all kinds of different ways to name stars, and some of them are in numbers and some of them are words and some of them are a combination of both. So now we're getting here to the point where I'm going to stop it right there. Now, if you look at that, we have quite the diagonal line here, and we also have the scale of color. So the ones over here are in nice order. They're blue, then they're lighter blue, then they're white, yellow, all the way down here orange, and then red. So as they go out, as this line goes from left to right, they get reddish. As it goes out, they get dimmer, and then they change in their color class as well. All right. So Hertzsprung and Russell called this the main sequence. And what they found was most stars appear on that main sequence. That's where they are for most of their lifespan. You see, stars when they form, many of them are really bluish and hot when they're formed. And then when they go through burning, burning isn't a great term, but we can just call it burning. As they burn through their fuel, they become more yellowish in color, and eventually they use most of the fuel and they become a red star. And that's kind of what most stars do. However, as with many things, let me start this again. You will see now as these other stars get plotted on this graph, and as they come in, they are not on that main sequence line. In fact, they're quite a bit off of the main sequence. And they don't play like the other stars. They are different. They are like oddballs. And so they kept plotting, and what they realized is that most of the stars still are along this this angled line that they call the main sequence, and but many other stars fall off of that main sequence. Some of them are down here. These are dwarf stars, smaller, and some of these are bigger. But just to give you an idea of how different they are than the main sequence stars, this star right here is called Betelgeuse, and Betelgeuse is a red giant star. Now, if it followed the pattern of these stars right here, the bigger stars would be brighter and hotter, but Betelgeuse is even bigger than Bellatrix is here. Betelgeuse is huge, and look, it's almost 1,000,000 times brighter than our star, and yet it's cooler. So, again, it's just an oddball. Most of them are along the main sequence, but a star like Betelgeuse, it doesn't follow that same pattern. Okay, so we have exceptions to the rule, and that's what Hertzsprung and Russell figured out. Now, you're going to see this graph more when you are in 8th grade, and you will study it in depth and really kind of break it down into more than what I just did. So you also probably will see some questions about this diagram on your MCA test when you get into 8th grade. So keep that in mind for the future. All right, so let's start our show for the day. And this show is called Sunstruck. And let me get this rolling here for you. Now, Sunstruck is all about stars, but mostly about our star, the sun. And if you listen very carefully, you will find the answers to the questions that are going to wind up at the end of this video. There will be 3 questions, just like yesterday, and hopefully you can pay attention well enough to understand those answers, understand those questions when you get to them, and come up with the right answer. All right, so I'm going to turn my camera off and get this show going, and we'll see you next time.
The sun It's one star among 300 billion in our galaxy. It's not close to the center of the Milky Way. It's not the biggest star, not the smallest, the brightest, the hottest, or the coolest. It's not even the only star with planets. Class G yellow stars like the Sun make up 1 out of 13 stars in our stellar neighborhood. It's not special in any way, except one. It's the only star we know of that supports life. The Sun is our star. Without it, Earth would be cold and dark. There would be no weather, no life. In fact, there would be no Earth. From the dawn of life and through most of human history, the Sun was a benevolent giver of light, heat, and energy. But now, as we rely more and more on technology, we're learning that our star is more dangerous than our ancestors ever knew. Like most stars, the Sun produces a lot of energy. It produces enough energy in 1 second to power human civilization for 500,000 years. Energy from sunlight enables life to thrive and multiply on the Earth. Nearly all life on Earth is supported by photosynthesis, the process plants use to convert sunlight to chemical energy. Animals eat plants and use that energy too. Those animals are eaten by other animals, and the energy moves up the food chain. The energy in the food you eat originally came from the Sun. Most of that energy is light. From low-frequency radio waves to high-energy gamma rays, light is much more than what we see. Visible light is one small part of the electromagnetic spectrum. Photons, which are the particles that make up light, travel in waves. High-energy photons make high-frequency light, like X-rays or gamma rays. Low-energy photons make low-frequency light, like radio waves or infrared. But how does the Sun produce so much energy? To find out, we must look deep inside our star. The Sun has 6 main layers. The outermost layer is the corona. This is the atmosphere of the Sun. It's much hotter than the surface and can be 1,000,000 degrees Celsius. That's about 1.8 million degrees Fahrenheit. Scientists aren't sure yet why it's so much hotter than the surface. It may be due to magnetic activity, but this is one of the big mysteries of the Sun. The next layer is the chromosphere. This thin layer goes from corona temperature to surface temperature very quickly. The visible surface of the Sun is called the photosphere. This is where all of the visible light that reaches Earth is emitted. It's also the coolest part of the Sun at 5,500 degrees Celsius, or 10,000 degrees Fahrenheit. Just below the photosphere is the convection zone. Here, hot material boils up toward the surface. The plasma at the bottom of the convection zone is around 2 million degrees Celsius, or 3.6 million degrees Fahrenheit. Below the convection zone is the radiative zone. Energy bounces around so much in this layer that it takes 170,000 years for a single photon to escape, even though it's moving at the speed of light. Finally, the core. The heat and pressure in the sun's core are so great that atoms of hydrogen are smashed together to form helium. This process is called nuclear fusion, and it produces the immense amount of energy that will fuel our star over the course of its 10 billion year lifespan. Energy leaves the core as photons. They bounce around the radiative zone for 170,000 years, boil upward through the convection zone, and are finally emitted from the photosphere. From there, the photons travel nearly 150 million kilometers, or 93 million miles, to the Earth in only 8 minutes. The sun emits light across the entire electromagnetic spectrum. But high-energy wavelengths like ultraviolet, X-rays, and gamma rays are incredibly dangerous to life on Earth. How can life survive all of that dangerous electromagnetic radiation? The answer is Earth's atmosphere. The envelope of gas that surrounds our planet blocks nearly all of the dangerous wavelengths of light. The visible portion of the electromagnetic spectrum, the light we can see, passes right through. So do some radio waves, microwaves, and infrared. They help keep us warm. In addition to heat, light, and energy, the sun also bombards the Earth with high-energy particles. These particles come from the corona. This is the solar wind, and it streams from the sun constantly in all directions at speeds of 400 kilometers per second. That's about 1,000,000 miles per hour. If the particles that make up the solar wind reached Earth's atmosphere, they would gradually strip it away, leaving Earth airless and unable to support life. Luckily, the Earth has a strong magnetic field that acts like a shield. It deflects most of the particles from the solar wind. As long as we stay on the ground, humans are fairly safe from the dangerous effects of our star. But with humans and technology in space, things are a bit more complicated. Scientists call conditions in space that affect humans and our technology space weather. It's driven mostly by the sun. Space weather includes the solar wind, as well as solar flares, coronal mass ejections, and geomagnetic storms. We're learning how to forecast space weather. To help, we have more than 20 satellites dedicated to studying the sun. But the most useful tool so far is on the sun itself. That tool is sunspots. Solar storms often start near sunspots, and solar storms affect space weather. Sunspots go through a cycle every 11 years where their number rises and falls. During solar minimum, there aren't many sunspots. Those that appear don't last very long, and solar storms are pretty rare. Solar maximum is a very different story. There can be as many as 100 sunspots on the sun at any given time, and they last for several weeks. Sometimes there are several solar storms per day. So why do sunspots appear? The sun has a large, powerful magnetic field. It extends throughout the entire solar system. This huge magnetic field is generated deep inside the sun, bursting through the surface in long lines and loops. The sun isn't solid, so areas rotate at different speeds, which twists and tangles the magnetic field lines. Sunspots form where the twisted lines emerge from the photosphere. Exceptionally strong magnetic activity keeps the plasma in these areas cooler, which is why sunspots appear dark. Strong magnetic energy around sunspots can drive solar storms. A solar flare like this one is a perfect example. A flare occurs when tangled magnetic field lines suddenly snap and reconnect. This releases a burst of electromagnetic radiation and energized particles, or plasma. Only the largest flares have any impact on the Earth. We're much too far away for the intense heat of a flare to ever reach us. Most of the problems that flares cause are related to technology. The particles and electromagnetic radiation from large flares can cause radiation storms in Earth's outer atmosphere. This might disrupt communication signals on Earth, anywhere from a few minutes to a few hours. Everything from TV signals to GPS, and even cell phones can be affected. Another type of solar storm is a coronal mass ejection, or CME. CMEs are more dangerous. Unlike flares, CMEs can affect technology on the ground. A CME is a bubble of plasma and magnetic field lines launched from the sun's atmosphere. They often start over clusters of sunspots. A single CME can contain billions of tons of material that smashes into anything in its path. The plasma in a coronal mass ejection is especially dangerous for spacecraft outside of Earth's protective magnetic field. Plasma is a super-hot, electrically charged gas. It can damage a satellite's onboard electronics, causing it to fail. Many times, the magnetic field in a CME will be repelled by Earth's magnetic field, similar to putting the north poles of two magnets together. But sometimes the two magnetic fields are attracted to each other. The result is a geomagnetic storm. Earth's magnetic field gets peeled back like an onion, and particles from the sun can reach lower into our atmosphere. This is what causes the aurorae, the northern or southern lights. A geomagnetic storm can also create ground-induced current. This is an electrical charge that travels through large conductors. Things like cars, airplanes, and even trains are safe, but power lines and water pipes aren't. Current traveling along pipes can weaken or even break them. Broken pipes might mean people have to go without water. And even though power lines are made to carry electricity, adding extra current is dangerous. Things like electrical transformers can break down. If that happens, it can take months to replace a single transformer. Parts of the power grid could be shut down. That means no refrigeration for food and medicine, no gas pumps or hospitals. Even running water relies on electricity. A CME might not physically harm you, but think about all the things you use every day that need electricity. CMEs aren't rare, especially during solar maximum, but they're only dangerous if they're aimed at Earth, which is rare. The last time a supersized CME hit Earth, the northern lights reached farther south than Florida. The telegraph system, which was the highest technology of the day, was disabled worldwide. Back in 1859, the effects were minor, but something that size hitting us today would be catastrophic. For most of human history, space weather simply wasn't a problem. It's ironic that the technology that allows us to study space weather makes us more vulnerable to it. But space weather isn't the only threat from our star. As the sun ages, it gets hotter. Anywhere from 1 to 2 billion years from now, the brighter sun will render the planet too hot for most life on Earth today. Eventually, it will be so hot, the oceans will evaporate. Water and air will boil off into space, and Earth will be too hot and too dry for life. Then, in about 5 billion years, the sun will run out of hydrogen in its core. It will expand into a red giant and get so big that it will engulf the orbits of Mercury and Venus, and possibly even Earth and Mars. As the sun works to consume as much fuel as it can, it will collapse and fuse helium into carbon for about 100 million years, until it too is exhausted. At the end, there won't be an explosion, no spectacular supernova. The outer layers of the sun will just drift away, forming a nebula that will disperse in about 10,000 years. That's the blink of an eye in cosmological terms. The core will remain as a white dwarf, spinning and dissipating heat until it eventually falls dark, billions of years later. It seems like such an uneventful end for the star that gave us life. But by the time the sun dies, humans might have moved on to other worlds in other parts of the galaxy. In its time, the sun will fuse elements like carbon, nitrogen, and oxygen, which are the elements of life. The sun will seed the universe with the potential for new life, just like older generations of stars did for our sun. It's a cosmic cycle. Maybe one day, humanity will witness new life on a new planet, orbiting a new sun. If that life is anything like us, they will look up to their own star and wonder.